Hi, everybody. Welcome to our panel on smart oceans, from tech to surf to seafloor. Just to let you guys know a couple parameters before we get going, we have a hashtag that we'd love for you all to use if you hear something really interesting from our panelists. The hashtag is smartoceans. Also, we're going to have Q&A for the panel as well. We'll have about 15 minutes left over for any questions that you want to ask our wonderful panelists. And then also, we'll be outside to answer any questions you may have if you want to connect with us afterwards. So stick around because we will too. So to introduce myself, my name is Lauren Ellis. I'm a producer for Seeker, a science media company based in San Francisco, California. And I get the good fortune of producing a series that takes audiences inside interesting labs, out in the field, to hear directly from scientists who are trying to understand our world better. And the one place that is calling out for more information are our oceans. This statistic always surprises me, but we've mapped the surface of Mars in higher definition than we have our own seafloor. And 80% is still unmapped and unexplored in detail. And this is why oceanographic data is so critical. How can we respond to changes if we can't see what's happening? So with the brilliant panelists that I'm sitting next to right here, that we're inventing new techniques, new technologies that are helping us see things in better detail. So without that, I'd like to introduce our panelists.
So my name is Dawn Wright. I'm the chief scientist of the Environmental Systems Research Institute, otherwise known as Esri, which is a geospatial mapping company. We produce geographic information system software. We also produce services and techniques for data science. And part of our company is ocean-related. So as chief scientist, I lead the research and development projects in that domain and also represent Esri to the scientific community. Even though we're a software vendor, we are also very involved in science. And I have a 20-year career as an oceanographer. I'm a marine geologist by training, so I'm a seafloor mapper, and I took my degree from UC Santa Barbara to get that training. I'm very happy to be here today.
Yeah, thanks so much everyone for taking time out of the busy schedule here to come and hear a little bit about smart oceans. My name is Phil Bresnahan. I'm a research engineer at Scripps Institution of Oceanography, part of the University of California, San Diego. I'm also the lead engineer for the SmartFin project, and I'm going to be talking a bit about that, so I won't get too deep into it at the moment. But in my roles at Scripps, I lead the engineering and applied science behind quite a few different projects, mostly related to chemical sensor technologies. And I'm interested in studying the changes to ocean chemistry as a result of anthropogenic or human activity, changes to our environment and our coastal and open ocean ecosystems as a result of the things that we're doing on land.
Okay, so let's get a sense of the challenges. So Dawn, as an oceanographer who's gotten the chance to dive with Alvin, a really famous deep sea submersible, what makes studying the ocean so difficult?
Well, for one thing, the sensors that we have that we're used to understanding in terms of mapping the planet, satellites. So we're all very familiar with satellite technology. We've seen Landsat, we've seen Sentinel, we see these images mainly on the news and the weather reports. But these satellites cannot see through the water. And so that's a big part of our problem. It's a problem, but it's also an opportunity, because then we need to actually go to the ocean to map the oceans in the equivalent detail. And we often use a different type of energy for that, which is acoustic energy rather than the electromagnetic energy that the satellites are using. And in order to use that acoustic energy, we must be either on the surface of the ocean on ships, which travel about the speed that you ride your bicycle. So imagine trying to capture the data that you need at that particular speed. We also have to have our ocean robots that many of you may have heard about, particularly in the prior panels. And these ocean robots can only go so fast as well with their sensors. So part of it is just the enormity of the problem given the sensors that we have. The other part is that this planet, as beautiful as it is 70% ocean, 70% water, so we have a lot of territory to cover. So that's part of the challenge.
Along with that, so Phil, you're a surfer and an engineer who spends a lot of time exploring our coasts. What do we know about the coastlines today, or how much do we do or do not know about them?
Well, one of the things that we know is that about half of the human population lives along the coasts, and in really crowded areas in some cases, in less densely populated areas. And so we're really tightly coupled to the coasts and the health of coastal ecosystems. Even if we live inland, we could still be really tightly coupled to them because of the oxygen produced by phytoplankton or the protein that we take out in the form of fish or kelps or whatnot. And one thing that we're really interested in is both how coasts are changing as a result of human activity, but also how those changes end up affecting us. How things like sea level rise will end up affecting areas. We have a very good understanding of sea level rise at a global scale. We understand that average sea level rise changes for the most part, but it's really a lot harder of a problem to figure out what's happening in smaller spatial scales and small temporal scales, meaning over smaller spaces, smaller times. It's a little bit harder to predict. You have to put a lot more computational power into those models to figure out what's happening on a region by region or a zip code by zip code basis. That's one thing. Understanding just the effects of storm activity and how that might erode the coastal bluffs and how that might affect the populations living there. If you live at the top of a hill overlooking the water, first of all, you're incredibly lucky, but also you're living in this area that is subject to a pretty high level of risk, and trying to get an understanding of the marine geology and the sediment processes happening there, how sand is moving back and forth. One thing that any surfer would pay a lot of attention to is sandbars. Sand is always moving back and forth. If you're surfing at a beach break, you know where all of the sandbars were over the last few weeks in a row and how they've changed from season to season, from year to year. And there are scientists at Scripps and elsewhere who are studying those processes and trying to get an understanding of how that affects water flow and, again, the sediment, the sand movement processes, how that will affect sea level rise. So those are a couple of the things I'm interested in.
Gotcha. And with all of those questions and all those data points that we're trying to gather, let's talk about how difficult it is to develop tech out there. What are some of the big obstacles that you have to overcome to even get something to work out in the ocean?
Well, my company works with the data that comes from the tech that's out in the ocean. And so one big challenge is how to transfer efficiently the data, the zeros and ones, coming from robots or from ships or from surf fins up into what we call the cloud, because a lot of the processes, the data analysis, the mapping is actually done in this mysterious thing called the cloud now. It's very, very efficient. It's basically just a bunch of servers that are in undisclosed places. And one of the big challenges is how to deal with all of the data so that we can understand, we can actually mine the data to pull out knowledge and interpretations from that. And then the next step, once we do that, is to actually present that data in ways that people understand, people beyond the scientific community. Especially if we want policymakers and resource managers and educators to really understand what it is that we have achieved and what it is that the data are actually telling us. And if I could just take a moment to illustrate the problem of too much data, because we talk about how little we know about the oceans and how we need more data, but in certain areas, particularly near the coast, with bathymetry, with mapping the ocean floor, it's actually a situation of perhaps a little bit too much data. And I'm going to use an analogy that a colleague showed to me, which I think is really fun. So most of the sonars that we use to map the ocean floor can map in terms of the amount of time that it takes for the sound pulse to go down to the seafloor and back, and that's a distance, and that gives us bathymetry. These sensors can also map the strength of that return, which is what we call backscatter, and that's how we get pictures of the ocean floor. And then they can also map the water column, or the water in between. And these sonars usually are collecting data at about 115 gigabytes per hour. So that's a 1.5 billion to 1 ratio. And if we take a marble like this, and this represents the amount of data that we're able to gather in 1 hour, and after a while, we're able to gather the amount of data that takes this little blue marble, and the blue marble becomes the size of the entire Earth itself. So that's the problem that we're dealing with in terms of big data, too much data coming in. So part of what my company does is to come up with techniques for making that data manageable. So it's a sort of an irony.
So the question of what are some of the tech challenges is kind of what I lose sleep over. You're asking me to describe my nightmares. As an ocean technologist, I spend a lot of my time trying to figure out how to overcome these challenges. One of the biggest ones is what we kind of all learn early on in our lives, don't mix electricity and water. And that's my full-time job, trying to put things that are powered into the water and make sure that they don't short, make sure that they don't electrocute anyone, including the fish out there, and make sure that they come back in one piece without fried electronics. And I'm not just saying that because it's a fun story to tell. I've seen quite a few circuit boards go out and do what they're supposed to do and come back, and they're just covered in salt water and crusty corrosion. It is a huge pain to keep the salt water away from the electronics. We have to come up with quite a few different mechanisms depending on what we're trying to measure to make sure that we're keeping the salt water separate. But when you're trying to put a sensor in the water to measure the water properties, keeping that separate from the water is obviously impossible. Another big thing is certainly pressure. The amount of pressure that things have to be able to withstand as they go deeper and deeper is just tremendous. I mean, anyone who's tried to swim to the bottom of just a 10 or 20-foot pool understands what it feels like in your ears. Imagine trying to send something that's going 100 times deeper than that, trying to make measurements the whole way and then come back to the surface and transmit all of that data to the cloud so that we have access to it from our home servers. So pressure, salinity, and corrosion, these are really big issues that we deal with every day.
And as you two have gone along sort of developing your own techniques and technologies, has there been an aha moment, something that you're like, this is it, this is the fix?
Surfers. So that's a good cue up to talk a little bit about the SmartFin project. One of the things that we spend a lot of time thinking about at Scripps is how to work with coastal communities to get a better understanding of what's happening out there, and how to communicate some of the changes that we're already aware of, but also how to collect more data along coastlines and how to figure out what's going on in these much smaller spatial scales that I mentioned. So that's one thing. And then just working with, there was this great panel just yesterday on ocean robots to the rescue, it was called. Working with all of the people who are developing new and innovative platforms and putting our sensors on those is one really cool way. So these collaborations where we have certain specialists working on robots, certain specialists working on sensors, certain specialists working on cloud-related issues, and bringing all of those different groups together has been one of the most exciting parts of my career so far.
And then to follow on to that, a big aha moment or a big aha development in our world with data is the idea that data can be transferred via services, web services. So you don't have to have data on a disk or in the old days on a tape or on a laptop. They can be transferred from the sensor directly to a satellite and then down to shore. And then those things continually live on the internet, in the cloud. And the wonderful thing about that is that once you have the data in the cloud, it can stay there. You don't have to be transferring these large data sets back and forth. But you take the analysis, the algorithms, the numerical recipes up to that data. So you've got one copy of the data, and then you can do all kinds of different machinations on that, make all kinds of different maps, all kinds of different analyses, all kinds of different interpretations, but it's coming from the data just staying in one place. And that's extremely efficient and helps us to continually add to that living library up in the cloud.
And with the cloud, we also have Internet of Things, which has just been a really big hot topic in oceanography. So can you give me an example of how IoT has made an impact in your respective fields?
Sure. So this is a very tech-heavy conference. I'm sure most people have heard Internet of Things about 100 times already so far, but I do want to take a quick step back and use what my favorite definition of the Internet of Things is, or as Cisco Systems defines it, the advent of the Internet of Things is when there were more things, devices connected to the Internet than people. The people meaning through your cell phone or through your computer. So the Internet of Things is the set of devices that are talking to the cloud other than what you're holding in your hand, basically. And so one of the great examples of this that doesn't always use the nomenclature Internet of Things is called the Argo program. And this is one of the most fascinating international collaborations in the field of oceanography, in my opinion. There are over a dozen countries involved in the International Argo program. And the way that this program works is there are these floats, these robots that are about my height that start at 2,000 meters below the surface, and they profile, they increase their buoyancy, and they float up to the surface, and they collect data the entire way as they're rising from 2,000 meters up to the surface. When they get to the surface, they have satellite antennas that allow them to beam all of the data back to land, and again to these cloud-based servers, so that we, scientists, have access to the data wherever those floats may be. There are already close to 4,000 of these out there just freely drifting, following ocean currents. They've, most recently in just last year, they completed their, I believe it was their 2 millionth profile, meaning the 2 millionth time that they went from 2,000 meters up to the surface, collecting data the whole way through. And this has been tremendously helpful at helping us understand ocean currents, ocean heat uptake. So 90% of the heat that is trapped by the excess greenhouse gases that we're emitting ends up being stored in the ocean. So the reason that the surface temperature that we experience on land hasn't increased even more is because the ocean is taking a lot of that up. And the Argo program has helped elucidate some of these patterns. So this is one really awesome application of the Internet of Things, these devices talking to the cloud and giving us insight into what's happening all over the globe.
And then another part of that is keeping track of the Internet of Things, keeping track of these robots like the Argo floats. And so what my colleagues and I work on are things called dashboards. So if you're looking right now at a dashboard that is helping the French office of the Argo program in Paris. This is part of the World Meteorological Organization, which also works with the United Nations and does their part on the European front in terms of tracking and maintaining the Argo floats. So this is a dashboard that shows you all of the nearly 4,000 floats that are in the oceans, but this dashboard also allows the scientists to keep track of each of those floats. So if you go to the next slide, shows that each of these dots is queryable, and this is all happening in real time. So even as a new float is added to this constellation, it will be part of this dashboard. There are also ways that you can query or you can get information on what the different models of floats are or the different countries that have contributed these floats, and also the parameters, the data that the floats are sending back, whether there's a malfunction there, the cycle in terms of how long these floats are in the water when they need to be switched out and so forth. So the idea of these dashboards, which again are in real time querying all nearly 4,000 of these robots, is also, I think, a really nice advance. I liken this to, so for instance, I just got a Ring system installed at my house. So I've got all these security cameras around my house, and I can whip out my cell phone right now and see what's going on in my backyard. So I've got my own dashboard on my cell phone, which allows me to, through that set of Internet of Things, see what's happening at my home in California. And I think this is sort of the same idea.
Is this platform available to anyone to see, or do you have to be a scientist to have access to it?
So this particular platform, this is a prototype that we at Esri have just built for the World Meteorological Organization Office of Argo. So it's for scientists at this point, but certainly for anyone who's interested in Argo, we're going to change the display of this so that the information is more understandable by non-specialists. But the point is that these types of displays, these dashboards, can be reconfigured to all types of different audiences.
And so, Phil, I know that the SmartFin also uses the Argo platform. Can you maybe explain to everybody what the SmartFin is and how it benefits from it?
Absolutely. So SmartFin is what I'm currently working on. It's a surfboard fin that allows me to actually carry it around, so please come up and check this out even closer after the panel if you have a little extra time. The Smart Fin is just a surfboard fin that does a little bit more than your standard surfboard fin. Standard surfboard fin might be made out of plastic or fiberglass or carbon fiber, and most surfboard fins for the non-surfers in the room are interchangeable, so you can take it out and replace it with a new set of fins whenever you want. Our particular design of fin has some oceanographic sensors in it, so that when a surfer goes in the water, they're able to collect data and contribute through the cloud, again, to our understanding of coastal dynamics. At the moment, the Smart Fin has a temperature sensor in it, GPS for position, motion sensor, and then it's communicating with the cloud through a cellular modem. So it has almost the same exact electronics that just about everyone in this room has at least one of, if not a couple of, in their pockets and briefcases and so on. And so it's able to communicate with the cloud anywhere in the world, anywhere there is a cell network. It has international global bands. The fin turns itself on when it goes in the water. Using that same principle I described earlier, it just shorts two electrodes and it knows it's in the water. When the surfer gets out of the water, the circuit is opened and it starts looking for a cell connection, transmits all of the data to the cloud, and then all the surfer has to do is keep it charged. And we're using this technology to try to get a better understanding of what's happening along the coasts, especially in temperature patterns. One example of that might be with the phenomenon of coral bleaching, where corals, when it gets too warm, the zooxanthellae will actually leave. This organism that lives in the coral that gives the coral its color will actually leave because the temperature gets too hot and the corals end up looking really white. We're looking through the clear gelatinous coral itself and at its white skeleton. And so a lot of really famous surf breaks happen to be where coral reefs are as well. And so we're trying to equip surfers at those breaks with this technology so that they can make measurements that help protect the ecosystem that they love so deeply and rely on for their own recreation, but also rely on the water quality there so that they stay healthy while they're out in the water.
It's incredible. So with all these different tech developments, how does a company like Esri handle all these different data points that keep coming in with entrepreneurs and innovators with their ideas?
So this is what we love to do, those of us who are data people, data scientists, because through the magic of spatial statistics and computer science, we have figured out ways of clustering these data. So if we can go to another video that talks about another one of the projects that draws from the Argo data, there is a 3D digital globe of the ocean that we've built, and it's called the Ecological Marine Units. And it's basically drawing from the data that come from Argo, but also data that come from other types of gliders or other types of robots, gliders, equipment that's been thrown over the side. The NOAA has a wonderful library or catalog called the World Ocean Atlas that has a 50-year record of all of these observations. And so what we've done at Esri, along with many other colleagues, is to take those 52 million observations, and we're using spatial statistics to cluster these data into real, homogeneous, three-dimensional regions underneath the surface of the ocean. So now we have, and if we could start the video, it'll show you how we go from, is it not starting? Oh, it won't go. Okay, we can go with this one, with this image, because what we're really trying to get to is to go beneath the surface. Most of the maps of the ocean that we see, even sea surface temperature maps, are just showing you sea surface temperature. But what about the temperature beneath the surface? What about the rest of the volume of the ocean from that surface all the way down to the sea floor? And so with the digital ocean that we've created, we are visualizing all of these properties as columns, so you can see the colored columns in the visualization here. And then we can also slice through those volumes that are represented, and we can see profiles that show us how the temperature and the salinity and the dissolved oxygen and the nutrients taken again from NOAA's World Ocean Atlas, what that looks like beneath the surface. So it's really fun. It's a little scary at first because it is a lot of data, but we're using a lot of capabilities in the cloud, and we've also moved into the realm of machine learning to handle that as well.
Could you expand a little bit on how machine learning is powering Argo?
So machine learning, it doesn't power Argo per se, but it helps us to manage all of that data. Machine learning is a way, it's really what the term means, where you start a computer on a path using an algorithm or a technique, and the computer repeats that technique and learns how to recognize features in the data based on a starting point. And as you continually run that particular algorithm or that method on the data, it learns so that it's able to actually recognize similar features in data that it's never seen before. And so this is also really wonderful for classifying things such as different types of species of corals, for coral reefs, for example.
And so with all this data analysis, how does this loop back to innovators like Phil? Like, how does your design change once you see the data that comes from Argo and these platforms?
That's a great question. I would say it's a way to help us figure out how quickly sensors need to be able to respond to changes. That would be one thing. So if you have a sensor that is only able to respond to changes, say, every 30 seconds, as this profiling float moves from the bottom, from 2,000 meters up to the surface, that process could take 10 hours, which is a really long time. But if you have a sensor on there that only responds to changes, say, every minute or so, it just has a lag time built into it, you're not actually able to see some of the finest scale changes in there. And so we often spend our time trying to make the sensors even faster and faster, and certainly more accurate and more precise. That would be one big thing. But then it also helps elucidate some of the gaps that we have in the parameters of interest. So you might see a change in pH from biogeochemical Argo. Biogeochemical Argo is the layer beyond the normal Argo that I described, where in addition to the normal Argo sensors of temperature, salinity, and depth, biogeochemical Argo also has pH and chlorophyll fluorescence and turbidity and nitrate, a couple other things, dissolved oxygen. And so trying to figure out what's happening to the biology, the chemistry, and geological processes that are happening there. So imagine you're making a measurement and you see a change in pH, and that might surprise a scientist in a particular area. You need to fill in, well, why was there a change in pH there? We invent a new sensor for something like chlorophyll. Oh, the change in pH might have been because there were more zooplankton or phytoplankton living there and consuming the CO2 or giving off more CO2 and changing the pH through the chemical processes that unfold there. So we're using everything that we learn to also ask more questions and then invent new sensors to continue down this path.
And Dawn, have you seen any changes or pivots from your point of view on this?
Well, it's interesting because as we develop new data science techniques, one of the things that we are trying to understand is how we can better predict where there are gaps, because despite the wonderful deployment of all of these robots, we're still not getting every single square kilometer or square inch of the ocean covered. So we still want to be able to predict what these parameters or these characteristics are going to be in between, in the gaps. So how can we interpolate between where we actually have measurements? And so this is where our techniques come into play. In fact, what you're seeing on the screen is one of the ways that we're developing now to interpolate what the ocean oxygen content is based on Argo data from that particular area, but also casts or individual measurements from other experiments in the water. And so we can take these isolated point measurements of oxygen, and we can stretch them out into surfaces. And so we are actually taking a very educated guess at what the oxygen level is across that entire surface. And then as we go down deeper into the water, we continue to make those educated guesses. And as more data are collected there, as there are more sensors that are put into, in this case, the Monterey Bay, those slices, those layers that you see going down deeper into the ocean, those are going to get more accurate and give us a better picture of maybe places where there's a low or minimum oxygen that's affecting the fisheries in that particular area.
Impressive. So when you're looking at this slide, the different colors are the levels of oxygen, just to clarify?
Yes, so the warmer colors are higher levels of oxygen, and then as you get deeper and colder even, the colder colors mean that there is lower oxygen there.
So as a forward-looking question for you both, what's next in tech development for the oceans?
That's a tough one. We didn't script that one.
Keep you on your toes.
Yeah, well, I think it's a combination of a couple of the things that we're talking about. I think we're really only scratching the surface of what we can do with machine learning and with innovating new sensors. One of the exciting frontiers in my world, I think, is the cheapening of sensors. And I don't mean the decrease in quality, but the decrease in cost that allows us to have more and more sensors out there for more different things. And using machine learning techniques on top of all of this new data to try to figure out what the data is actually telling us. So the numbers themselves aren't actually all that valuable unless we can extract some certain amount of insight from it. So inventing sensors is a great thing, but we have to combine the sensors and the data output with some parameters that we're really interested in that ultimately, in many cases, tie back to human health or the better understanding of fisheries, as Dawn mentioned, so that we understand where the fish are living. And one really important phenomenon right now with all of global change in general is getting a better understanding of how quickly organisms are able to keep up with those changes. So in the earliest days of oceanography, if you were at the last panel in this room on ocean exploration, they talked a little bit about the history of oceanography dating back to the HMS Challenger expedition. And back then it was sort of just getting single snapshot measurements of what was going on out there. And throughout the last 100 years or so, it's been figuring out, oh, we actually are definitely doing something to the ocean, to various different ocean properties through human activity. Now I would say our current phase in oceanography is figuring out how things are responding to those changes that we're beginning to understand, and even more so, how to predict what's next. And that's a big place where machine learning can come in the predictive capacity, and improving models, figuring out what's happening in between the measurements that we do have, and helping us determine where else we need measurements to improve those models.
And it's great that Phil is mentioning machine learning, because it really is the next big frontier on the data front. We've been saying machine learning, that's actually a part of artificial intelligence. So in my world, when we talk about artificial intelligence, machine learning is a technique within that broader rubric of artificial intelligence. And then you can get even deeper into that with smarter machine learning, which is called deep learning. And so for a lot of us who are working with these data algorithms, we're trying to get the machines to be even more predictive, and to use networks of numerical recipes to improve their intelligence. And so we're calling that deep learning. So we want to be able to translate the deep learning directly to sensors, so that sensors are better able to calibrate themselves, and as Phil mentioned, to make some predictions in terms of what these sensors expect to find over let's say the next several months or the next several years within a particular study area. And then another part of what is on the big frontier is to actually make things easy, to make computers easier to understand, to make maps more intuitive, so that you understand what it is that you're seeing right away. And we realize, I mean, this is a whole research field in cartography. To make something easy and visually compelling is not easy. So that is also a very rich area of research that's still on the frontier for us.
Which is a great segue into visualizations, which is powering a lot of our presentation and also all the visuals you're seeing up here. So what goes into making a really great map or a really great piece of data that people can understand?
Well, I can say from the map standpoint, color. There is a thing such as color theory, so that you have the right hues and shading of color that makes it immediately intuitive for people looking at the map. So you were asking about the colors and the layers as we go down into the deeper parts of the ocean. And so the idea of going from warm colors to cold colors is something that took a lot of development over the years by many oceanographers, hearkening back to another history lesson for you, to Marie Tharp, who was a wonderful geologist in the 1940s and 50s and 60s who paved the way for oceanographic cartography. And she was a remarkable woman who was trained not only in geology, but in mathematics and art. So part science, part art is what makes a great map.
I can definitely corroborate that answer as a red-green colorblind person. I have a very hard time looking at a lot of scientific presentations and interpreting what they're trying to show. And one of the interesting things that we've learned in the SmartFin project is that evidently not everyone interprets maps the same way. Not everyone thinks about data the same way that specialists in these scientific domains would. And working with the surf community has been extremely informative in getting us to get better and better at displaying our data so that people who don't necessarily have the expertise or who aren't used to looking at maps of time series of data, for example, and seeing these things day after day, are able to actually get a better sense of what's happening out there. So here's an example of one of the data visualizations that we did with SmartFin, where you're looking at a video recording of a surfer with the SmartFin, and overlaid on top of that is the time series of data collected. In the very top panel, you have the acceleration that the surfer is experiencing, measured by the motion sensor. And then if you take the integral of the acceleration, you get velocity, so the speed that the surfer is going in miles per hour. And then on the bottom panel, we have the temperature. And so as the video progresses, you can see the red dots fill in those time series, and you can actually see the parameters changing as the surfer is catching a wave and riding in closer to shore, riding into shallower water. And so this is just one example that it's not necessarily teaching us a new thing. This visualization in and of itself did not teach us a new thing about how coastlines behave, but it really helped us work with the surf community and get them more excited about what we're working on and get them to go out and become the next group of communicators to talk about ocean changes that we do understand. So we've put a lot of thought into how to differentiate the visualizations that we might put together for a scientific community versus what we might put together for a surf community or any other group. Here's another example. This uses some of the color theory that Dawn was mentioning and a color spectrum that changes its luminance, so the colors get brighter as the temperature gets warmer. And you're seeing the evolution of the SmartFin project as we distributed these fins across the world. And as everyone went out for a surf session and recorded data, a new dot shows up for the average data. The temperature here is in degrees Celsius. Actually, it says that, pardon me for that. But it's showing the evolution and the spread of the project over the entire globe. So you can see we start in Southern California. That's where that first dot shows up. And then every frame represents another 2 weeks in the project's history. And so most recently we have spread, certainly not even close to every country, not even every continent yet, but we're getting to the point where we're working with communities in England to help understand what's happening with the satellite measurements that they're making. They're using the SmartFin to corroborate their satellite data, and working with a group in Australia to improve their marine ecosystem models to understand how fish are utilizing different parts of the ecosystem with this higher spatial data. So these are just a couple examples that we're starting to put together to hopefully improve our data visualization.
And as you work with different communities, are you finding the questions are the same? Is there a through line, or do different communities need different things as they experiment with the data and the SmartFin itself?
Oh, absolutely different concerns everywhere. Certain groups might be interested in maybe there's a new power plant that is being proposed for that area, and they're trying to understand what effect that's going to have on water temperatures, and then what different things might come to that area. Just where I surf, one of the hot topics right now is a desalination plant, and how the changes in salinity when they pump the extra salt back into the water, how that's going to affect the ecosystem there. So we're working on salinity sensors on SmartFin so that we can make measurements of that. And then one thing that we can learn from the GPS data, people are always asking us to try to help them understand how surf breaks are changing, just where they go on a day-to-day, week-to-week, month-to-month basis. And we can use the GPS data to help understand phenomena like sea level rise and coastal development, how that's actually affecting the wave quality in different areas, which might not sound like the most scientific endeavor, but it's actually because of these changes that we know are happening, and we're trying to help put the pieces together for these communities.
And if I could add just another tidbit to this, Phil's research on wave quality and understanding wave dynamics is also part of a burgeoning alternative energy industry, I would say, because before I moved to California, I lived for many years in Oregon, and Oregon is really at the forefront of developing buoys that will actually take the energy from ocean waves and turn them into electricity, and they have a couple of test sites that are working on that now. So that's what they hope is the future of their alternative energy business development for that state. And so this type of research is extremely important beyond the science as well.
This is a bit of a tough question, but as a prediction, how close do you think we are to fully understanding everything we need to know about our oceans? How much more do we need to know? We won't quote you later.
Well, as an oceanographer who wants to keep getting funded, I'd say we'll never know everything that we need to know. But certainly one of the things that's exciting, and you may have heard about this in the other panels, is this idea of having all of the ocean floor mapped at the same resolution as we have as our street maps, for instance. So this is the Seabed 2030 initiative. And so by 2030, we do want to have this comprehensive, very detailed map of the entire ocean floor. And so we're trying to, that particular initiative, which involves NOAA and many other governments, nonprofits, fishermen who are crowdsourcing the bathymetry, they're all mobilizing and coming together so that we can achieve that by 2030.
Well, I don't want to be too much of a downer, but one thing I've learned as a chemical oceanographer is that every time we learn about a new source of pollution, the groups that might be causing that pollution are already moving on to the next pollutant, and we're kind of constantly replacing pollutants with new pollutants, and hopefully we can start to catch up to that as scientists, as a scientific community, and ultimately have the proper regulations in place so that that's not an ever-going problem. But to get to your question of how close are we to knowing everything, just in my relatively short career in the field of chemical oceanography, I've seen quite a few new hot topics come along just because we're creating new substances that we don't understand. We don't understand their downstream effects, and we're constantly innovating, which is what we're probably all here for this week, which is awesome, and we're coming up with solutions. But sometimes those solutions come with side effects and their own sets of problems. So there's a bit of career security, to get back to Dawn's point, related to that, which, again, I don't mean to be a downer about it, but there's also this fascinating panel today, or a presentation by Franz Cordova from the National Science Foundation, where she was talking about navigating the new Arctic. And I think that's a really exciting frontier. I think that we're literally opening up passages that haven't been open for maybe tens of thousands of years or longer. And so there's so much new science to be done in these areas. Another thing is in getting smaller and smaller in our understanding of biological phenomena, for example. So as we get these better technologies, we can start to take pictures of smaller and smaller organisms, for example. So one example of this is a Scripps-based phytoplankton camera system that's actually in situ. So for probably about a couple hundred years, people were looking at the smallest creatures living around the world through microscope slides, and we'll probably be doing that for as long as science is around. But to look at something under a microscope slide means that you actually have to take it out of its natural ecosystem. In doing so, you're changing the environment that it's in, and maybe you're crushing a gelatinous, a little jelly organism or something. And so having an in situ camera system like the one for the images that we're looking at the moment allows scientists to take pictures of things in their natural environments and get a much better understanding. And this is only possible due to the advent of new technologies in optics and then in deep learning, for example, to start to classify some of these. There have been over 1 billion of these images collected already from just this one camera system. And imagine if you put these camera systems up and down the coasts all over the world or out in the middle of the oceans, how much more we'd understand about phytoplankton blooms and harmful algal blooms, for example, and the sources of food that the fish that we are relying on for our own food are relying on in turn. So I started off on maybe a bit of a downer note there, but I think there are these really exciting opportunities for us too. And it's, I think, are we close to learning everything? No way.
Okay. Well, on that hopeful note, I think we'll just open up the floor to any questions. Does anybody have anything you'd like to ask the panelists?
Hey guys. Phil, I'm from Mauritius and I spotted that there's only one dot in the Indian Ocean, so maybe we have to talk later. Basically, I have a really quick question. We're a developing nation, we're by the sea, around the Maldives, the Seychelles, they're all going to get heavily impacted, and it's a beautiful part of the world in terms of sea. So my question is, how can we possibly start getting more data on the impact of industry, et cetera, because at the moment we're seeing everything from up above and we're kind of guessing that it's not great, or maybe, fish population or marine population is decreasing, but we simply don't have a clue. Thank you.
Thank you. Yeah, we'd love to get some surfers in Mauritius using the SmartFin technology, and I would love to talk to you more about that. To your other question, I think there are a few different ways to approach it. One way is using satellite technology, which has this just incredibly rich data set, or sets of data of all different sorts, and it's all just freely available from NASA, from the EU, from Japan, quite a few different space agencies that are releasing all of this information. And so it doesn't depend on people in certain areas actually deploying their own sensor networks or actually doing their own on-the-ground monitoring or on-the-water monitoring. So it opens up this whole new world of possibility for people that have access to a certain amount of computational power. Again, that's not to be taken as a given, but that's one opportunity. I think getting back to something I mentioned earlier on the less expensive sensor technologies, I think this is where we stand to make really big gains in really making these sensors less expensive and easier to use, so that it doesn't rely on highly trained scientists in every case just to deploy the instrument. We want to make these things so that they can be much more pervasive, get them out there, and get them into the hands of the people who have vested interests like you're describing, and can actually, they have this motivation to understand what's going on out there. It's more than just an academic interest. And so coming up with some new technologies that don't cost hundreds of thousands of dollars and don't require years of training in a PhD program to know to operate. So I think the less expensive sensors, citizen science opportunities all offer some good ways forward, hopefully.
And just an additional tidbit, Phil mentioned the satellite data, which is a wonderful source. And there are also other oceanographic data catalogs that are available for the Indian Ocean and around Mauritius. And those are available mainly through the United Nations. And then also at Esri, we have one of the world's largest digital libraries, which includes oceanographic data from all of the oceans. And then finally, there is a wonderful initiative. So Esri is a corporate partner of Scripps, and another corporate partner is Sail Drone, which is a wonderful group that is deploying catamaran, wind-powered sail vessels that don't have people on them but have tons of sensors, and they're collecting data in the Indian Ocean all the time and making that data available.
And I can just add one last thing, which Don reminded me of, which is that there are a lot of graduate students out there who are hungry for research projects that have direct real-world applications, and getting in touch with the communications offices and the academic leaders at different institutions that can help find the students who are kind of still lost in figuring out what they want to do with their careers. I was there not all that long ago myself, and would have loved to have known that someone was eagerly looking for answers in a particular ecosystem, in a particular region. To know that the science that I was working on had that direct real-world application would have been amazing. And I'm sure there are hundreds or thousands of other people out there in similar situations.
Hi. On behalf of South by Southwest and the ocean, thank you for being here and trying to help us all. And
Thank you.
along 2 or 3 things you just said, Don, we've talked a few times, but the Esri project and the UNESCO Decade of Ocean Science, if you can kind of tell us kind of what that is, because the whole mapping and putting the layers of data on the maps is important, one. The other thing is the sensors, size and cost and stuff like that. I just met with some Texas State students that are got a float thing that they're working on. You guys should probably want to connect them. And also a group from, I want to say Dubai. I'm going to send, I have your email, so I'll send it to you. It's in the trade show over there. I want to say it's Dubai or one of the Middle East countries. Think of a Band-Aid, a round circular Band-Aid, a circuit board, a controller board, and a battery all fit in that submersible, thin, blah, blah, blah. Anyway, so that's way cool technology that fits in all of our things. So again, thank you for being here, and I'll get you that information.
Yeah, thank you. I'm so glad you mentioned the UN
Hear
Decade.
about the UNESCO Decade of Science. That's my main question.
Yes, well, it's actually broad across the entire United Nations. So hopefully everyone in the room has already heard of the United Nations Sustainable Development Goals. The Sustainable Development Goals are follow-on from the Millennium Development Goals. They're more comprehensive in that they are not just about small developing nations, they're about all of us taking the steps needed to eradicate poverty, to help all people get educated, to mitigate climate change. And SDG 14 is the Sustainable Development Goal about the ocean and about protecting the ocean, about sustainable fisheries and all manner of wonderful things that we need to do for the oceans. The United Nations is actually pushing forward SDG 14 in a number of ways. That's the only SDG that's had its own conference thus far, the UN Ocean Conference. And the United Nations will be launching a decade of ocean science in support of sustainable development. So it goes beyond UNESCO to all of the other parts of the United Nations. It's a very broad effort that's pulling in Scripps. So the director of Scripps, Margaret Linen, is on the executive council of that effort. And this is going to be, we hope, a wonderful thing that everybody hears about. I was so struck by what Jyotika Ramani said in the prior panel about how in 2012 we all knew about the robot that landed on Mars, and yet we knew almost nothing about the famous Hollywood director who went down to the deepest part of our own ocean. And so this UN decade of ocean science for sustainable development is going to try to make a big splash. Also because we're running out of time. We're running out of time to save our oceans and to reverse, if we can, some of these effects, such as ocean acidification and low oxygen in the ocean and so forth. So you'll be hearing and seeing a lot more, mainly from the UN Directorate, but also from, I think, all of the oceanographic institutions, many, many universities, where we're all going to be talking about this UN decade. And maps will be a huge part of this. So Esri is one of the companies that is in strong support, and we've already been building dashboards for the United Nations so that they can track progress on their sustainable development goals, including our favorite SDG 14. And by the way, there's 17 of them.
think it's really awesome to hear all of the talk around the SDGs lately. I think it's really nice as a scientist to have some set of unifying principles that we can use. There's so many people that I think are interested in coming up with solutions to many of the known problems and don't always know where to look, sometimes because there's so many problems, there's so many interesting phenomena that we could be looking at, but it's great to know that there's so much energy going into this initiative. I've heard probably 5 different panelists mention the SDGs up till now, and I just think it's amazing that as a scientific community with so many diverse backgrounds and diverse interests that we're starting to unify around some of these principles to come up with problems, to come up with solutions.
Yeah,
We have plenty of problems.
there are problems that come from the solutions, yeah.
Hi, I'm Tom. I'm not a scientist, and to me it sounds like there's a lot of research going on. It's kind of like very foundational. Let's gather a lot of data and see, if some patterns are emerging from that. And I'm wondering beyond that, what are some specific research questions that are kind of captivating your society? Drawing an analogy, for example, in global health, it's seems like a lot of funding goes into malaria specifically. I'm wondering if there's like an analogy in your field where most people agree that that's something we should focus on. Thank you.
Well, I think in the mapping realm, again, one of the big research questions is how do we democratize data, and how do we democratize the ability to understand and to analyze data so that it's not only for people who have PhDs. So this is a very difficult thing to do. So if we want to be able to do for ourselves and our community, such as mapping out places that should be protected, or where to build the next schools or parks, or where should we put a landfill so that it's not making people sick. These are questions that communities need to be able to answer for themselves. And so one big research question is, how do we create the best technology to let people make those types of really important, complicated analytics themselves, often in concert or collaboration with scientists, but in ways that are more automated and that are also rigorous. And also, and this rigor means that we also need to be able to produce maps that show uncertainty and error. This is a long-standing research question. It's a holy grail. You see maps all the time. I rarely see maps that show how uncertain or how much error is in the map. Everything is rosy, everything is correct. If it's in a computer, of course it's right, and so forth. So these are some of the nightmares that keep me up at night in terms of the mapping world.
Yeah, I think the scientific community is getting much better at understanding that we can't just answer questions that society is handing us with read this paper, it has all of the answers, that has the global projections for sea level rise around the world, and we have the models, it's fine. Communities will often ask, how is that going to affect us specifically, and how is it going to affect us not in 2100, but how is it going to affect us in 2025 or even 2020 if there's some major storm event. So one of the unifying things that I've noticed more recently, to jump off of what Dawn was saying, is the distillation of meaningful information and things that people can actually take action on, and not just trying to send out a set of PDFs for people to read at their own leisure that probably have so much technical jargon that only 5 people in the world can understand them, but actually distilling the information so that you can immediately decide, how does this affect me, whether I'm living in some beachfront property and want to know if it's going to get washed away by a storm, or live near a particularly productive coral reef and want to understand how the fish populations might change there. So I don't know if there's a single topic that really unifies us, because we have so many different interests, but the way that we're trying to communicate the changes that we're learning about That I've definitely seen change in the relatively short time that I've been around, and that's a big, big push so that we can get people the answers that they need.
When it comes to the, first of all, thank you for a great panel. When it comes to the development of tech and data collection, when it comes to the ocean, I'd be curious to hear more about the kind of ecosystem and maybe partnerships between academia, government, the private sector, where there's seemingly more entrepreneurship in this sector, what you're seeing there and what's encouraging or interesting or maybe annoying.
Well, I can quickly talk again about this ecological marine units project that we've been talking a little bit about, because that's an example of a public-private partnership. It was commissioned, that this 3D digital ocean was commissioned by a United Nations of sorts, of countries and organizations that are interested in building a global Earth observation system of systems in order to solve 9 different societal problems. And these kinds of things, it's not like Lord of the Rings. It's not one ring to rule them all. It's not going to be just Google building this, or heaven help us, Facebook, or just one entity. These things take a very broad partnership. So the Ecological Marine Units Digital Ocean, we talk about that as an Esri product because we're hosting it, but it came together because of the U.S. Geological Survey as a government agency that was coupled with universities who were involved, and then there were also nonprofit conservation organizations. So that was a nice example of government partnered with industry, partnered with academia. And I don't find there was nothing really, it's been one of the most wonderful collaborations. There's been nothing annoying that we've seen about it. It's been absolutely wonderful to have all of those different perspectives come together. And with industry involved, people often think that, well, we have to be able to make money out of this. And no, that's the last thing that we are thinking of. I think a lot of the companies, like my company, we are just as frightened about the future as everybody else, and we're just all trying to get to solutions quickly before time runs out. And so the idea is to get this solved, get the data out, get it in the hands of people who need it, and let's get going to solve this because it's that important. So that's just one example. There's so many more.
Do we have time for one more, or no? I don't. One more. Okay.
Monica's my best buddy over there. Thank you. So this is more in the way of an endorsement of what Don just said. Not every company is like Esri, but what they're doing is huge because you've got to have a common data language. You know, if you're collecting these data, you have to organize it in a way so that everyone knows what you're talking about. So I just want to, from a NOAA perspective, I want to endorse and express appreciation to Esri for taking leadership on ecological marine units and in other areas so that we do have a common language. NOAA can't do it, USGS can't do it. We need this kind of partnership to make it all work for all of us. So it's critical. Thank you.
Okay. And with that, thank you all for joining us. Really appreciate it.